Welcome to the video on implicit differentiation, rates of change, and optimization. So first we have implicit differentiation. For this, you take the derivative of each component with respect to x or some other variable. Then if you're trying to solve for y, you'll put every term with dy dx on one side of the equation and every other term on the other side of the equation. And you can factor out and solve for dy dx. So this is if you want to solve for dy dx. So here we have an example. We want to take the derivative with respect to x of this function here. So you'll go component by component. So our derivative of 4x squared would be 8x to the first. And since this was x that we took the derivative of, it would be dx because we took the derivative of x with respect to x, and that just becomes 1. Then we have 3 times 2 is 6, y squared. Since we took the derivative of y, this will be dy dx. Then we have plus, the derivative of y is 1, and then we have dy dx, because we used y, equals, this would be 3 dx dx, which is 1, minus 0, because your constant goes away. So then this is 8x plus 6y squared dy dx plus dy dx equals 3. So if we wanted to solve for dy dx, we could subtract 8x from both sides, and that would give us 6y squared dy dx plus dy dx equals negative 8x plus 3. We could factor out a dy dx on the left side. So we'll have 6y squared plus 1 equals negative 8x plus 3. And then we divide by 6y squared plus 1. And we get that dy dx equals negative 8x plus 3 over 6y squared plus 1. So that's how you would solve for dy dx using implicit differentiation. Next, we have our related rates of change. For this, you'll solve for an unknown value using implicit differentiation with respect to time. So you'll use d dt. So in this example, it says, given that 3x minus 2y squared plus z equals 10, find dz dt when x equals 3, y equals 2, dx dt equals 2, and dy dt equals 4. So we have 3x minus 2y squared plus z equals 10. We're going to do the derivative with respect to time, so d dt. So we'll take the derivative of our first term, which would just become 3 dx dt, because we took a derivative with x. Then we have minus 4y, and this is dy dt. Our derivative of z would just be plus 1 dz dt, and that's going to equal the derivative of 10, which is just 0. So we know x is 3, y is 2, dx dt is 2, and dy dt is 4. So we have 3 times dx dt, which was 2, minus 4 times y, which is 2, times dy dt, which was 4, plus 1 times dz dt, and that's what we're solving for. So that equals 0. So we have 6 minus 32 plus dz dt equals 0. 6 minus 32 is negative 26. So we have negative 26 plus dz dt equals 0. So if we add 26 to both sides, we get that dz dt equals 26. So that's how your related rates of change work. Next is optimization. So we've learned about this in a previous video, so we'll just touch on this a little bit more. This is where you test to find where a certain value, such as length, area, volume, cost, or whatever, will be maximized or minimized. And the important thing we want to note in this video is that the best value might be one of the endpoints. So you always want to double check your endpoints to see if that's the best value for minimizing length or maximizing area or something. So here we have our first IB practice question where the calculator is allowed. It says, a farmer is using 24 feet of fencing to create a space for the chickens. He is planning to make 2 square enclosures. How much wire should be used for each square enclosure to maximize the total area? So he's planning to make 2 square enclosures. So we'll label the side lengths on this first one S and on the second one X. So we're maximizing area. So our area is going to equal the area of this first one, which would be S squared, plus the area of the second one, which would be X squared. So we have 2 variables here. We want to make it into one variable, so we'll look at our constraints. It says there's 24 feet of fencing. So 24 would be the total perimeter. So for this first one, the total perimeter is 4S. And for the second one, it would be 4X. So 24 has to equal 4S plus 4X. So we can solve for one of the variables. We'll solve for S by subtracting 4X from both sides. So we have 24 minus 4X equals 4S. And then we can divide both sides by 4. So we get that 6 minus X is equal to S. So we can go ahead and substitute this in for S up here. So our area equals 6 minus X squared plus X squared. So this equals 36 minus 12X plus X squared plus X squared. We can simplify that to 36 minus 12X plus 2X squared. So we're trying to maximize the area. So we'll take the derivative. So A prime equals the derivative of 36 is 0. Then the derivative of negative 12x is just negative 12. And the derivative of 2x squared is going to be a positive 4x. So a critical value will occur when this is equal to 0. So 0 equals negative 12 plus 4x. We'll add 12 to both sides and then divide by 4 to get that 3 equals x. So we'll have a critical value when x is equal to 3. So we want to find out if this is a maximum or a minimum. To do that, we could check the slope before and after, or we could look at our second derivative. So our second derivative would be the derivative of a prime, and that's just going to be 4. So since this is greater than 0, our function is going to be concave up because it's positive. Concave up looks like a cup, so like this. So what we have here is actually a minimum. So this would be how they minimize area. So we definitely don't want our side length to be 3. So now we'll look at our endpoints. Our total perimeter has to be less than 24. So 4S has to be less than or equal to 24. And 4X has to be less than or equal to 24. Those are 2 more constraints. So this means that S has to be less than or equal to 6, and X has to be less than or equal to 6. They also can't be negative. So it would have to be between 0 and 6. So we'll test our endpoints. So if S equals 0, our total fencing still has to be 24. So 24 would equal 4 times S, which is 0, plus 4 times X, which gives us that 24 equals 4X. So X equals 6. So if X equals 6 and S equals 0, our area will equal S squared, so 0 squared, plus 6 squared. So our area would equal 36. If S equals 6, then it's basically going to be the same thing because we have 2 squares, so they're the same shapes. So in this case, X would have to be 0. So ultimately, it would come out to the same thing of 6 squared plus 0 squared, which is 36. So at our endpoints, we get an area of 36. When X was 3, we had two 3x3 triangles because 6 minus x equals s. So that means that 6 minus 3 is s, and s is 3 as well. So that total area will give us 3 times 3, which is 9, plus 3 times 3, another 9. So that would have been an area of only 18 feet squared. So the farmer should make one square enclosure that's 6 feet by 6 feet. The other square enclosure should be 0 feet. In other words, it shouldn't exist. In order to maximize the area. So that's the solution to this question. Now we have our second IB practice question. It's no calculator. It says a 15-foot ladder is leaned against a wall. Suddenly, the ladder is slipping so that the base is moving away from the wall at a speed of 0.5 feet per second. How fast is the top of the ladder moving down the wall when the base of the ladder is 9 feet from the wall? So we have a triangle. This is your wall over here. And this is your ladder. And this is the floor. So it's a 15-foot ladder that's leaned against the wall. It's slipping so the base is moving away from the wall. So it's going this way. We'll define that way as positive at a speed of 0.5 feet per second. So we'll label this side as x and this as y. So our dx, dt, the speed the base is moving along the floor is 0.5 feet per second. How fast is the top of the ladder moving down the wall? So this way is going to be positive down the wall. And we're trying to find that speed, which is going to be dy dt, when the base of the ladder is 9 feet from the wall. So x equals 9. So we'll start with our basic equation to relate the three lengths to each other. So we have a right triangle, so we use Pythagorean's theorem. So we have x squared plus y squared equals 15 squared. So our derivative of that is going to be 2x. We took the derivative of x with respect to time, plus 2y, the derivative of y with respect to time, and that equals the derivative of a constant, so that equals 0. We know dx dt, we know x, we don't know y, and we're trying to find dy dt. So the way we can find y is by plugging in x to our original equation, so that we can find the distance the ladder is up the wall when it's 9 feet away from the wall on the base. So we have 9 squared plus y squared equals 15 squared. So 81 plus y squared equals 225. When we subtract 81 from both sides, we get that y squared equals 144. So y is going to equal the square root of 144, which is plus or minus 12, but we're not going to have a negative distance, so it's going to be 12. So now we know y. So we have 2 times x, which was 9, times dx dt, which is 0.5, plus 2 times y, which was 12, times dy dt, and that has to equal 0. So 2 times 9 times 0.5 is 9. 2 times 12 is 24. Then we'll subtract 9 from both sides. And then we'll divide both sides by 24 to find dy dt. So this says dy dt equals negative 9 over 24, If we divide both by 3, we get 3 over 8. So this would be negative 3 over 8. We defined down as positive, so this is actually going to be positive 3 over 8 according to our diagram. So the ladder, or the top of the ladder, is moving down the wall at a rate of 3 over 8 feet per second. And that's it for this question. So in summary, implicit differentiation with respect to x requires taking the derivative of each component with respect to x, putting every term with dy dx on one side of the equation and every other term on the other side of the equation, factoring out your dy dx and then solving it for dy dx. For related rates of change, you solve for an unknown value using implicit differentiation with respect to time. For optimization, you test to find where a certain value, such as length, area, volume, or cost, will be maximized or minimized, and the best value might be one of the endpoints. That's all for this video. Thank you for watching.